Hello everyone and welcome to lecture. Today we'll be talking about an introduction to multivariable functions, and specifically we'll be talking about how to visualize them using various tools. So in my introduction to multivariable calculus video, I talked about many different applications for why we might want to consider multivariable functions. And in this lecture, we're going to be kind of digging a little bit deeper into exactly what a multivariable function is. And we have a specific notation for a multivariable function. We see that f is a multivariable function if it maps points in n-dimensional space to points in m-dimensional space. And we have a notation for n-dimensional space and m-dimensional space, and we actually have a nice notation for what a multivariable function is. The notation is the so-called mapping notation. You put f with a regular colon, and then r to the n with an arrow, and r to the m. And what this is saying, if you kind of read this notation, is it's saying that f is a function that maps n-dimensional space to m-dimensional space, because Rn, n-dimensional space, can be thought of as multiple or n copies of the real number line. For example, R2 is just the normal plane, you have one x-axis for the first copy of the real number line and one y-axis for the second copy of the real number line. So it's similarly, R3 is three-dimensional space, because you have three separate copies of the real number line. One x-axis, typically we draw a y-axis like this with a y-axis. You can visualize it as going into the page, so this is three-dimensional. And the z-axis is going up like this. If you take your right hand and point make sure all of your index finger, your thumb, and your middle finger are perpendicular to one another, you can visualize the x-axis as pointing along your index finger, the y-axis as pointing along your middle finger, and the z-axis as pointing along your thumb. So there's no need to stop at three dimensions, and we saw in our examples that in general functions of any dimension are important, many different dimensions. But what we're going to focus on for at least the first part of this course is just functions from n-dimensional space to r, the real number line. These are called scalar functions. Because these are the mappings that are most easily understood when we were first starting kind of thinking about what a multivariable function is. So these are going to be mappings from n-dimensional space into R. they're called scalar functions, or sometimes scalar valued functions, because you're taking a point in a multi-dimensional space and you're getting out a point just along the real number line, so you're getting out a value. Specifically, we'll consider when n equals 2, so two-dimensional functions. So for example, of a function of two variables, you can come up with a number of different examples, but the idea is that we'll just do f of x y is equal to x squared minus y squared, or say f of x y is equal to sine of x times y, and you can come up with a number of different other examples. Same thing for n equals 3. We'll also be considering scalar valued functions of three variables. So this means that f depends on x, y, and z. And for example, you could have something like x squared minus y squared plus z squared, or f of x, y, z is equal to maybe sine of x times y times z. There are many other example functions that you come up with in either scenario, but the idea here is that we're always associating an input to an output, and the idea is that for a scalar function, the input, a scalar function of n variables, the input's a vector of n values, x1, x2, all the way to xn. In the output of this function is just whatever the function value is. Very often I'll say that w is the output, so we'll just use w as a symbol, and this is what the book does. And this is equal to whatever the function is of x1, x2, x3, and so on and so forth. So for example, in the case of a scalar function of two variables, right, the input is the coordinates x and y of the point that you want the function at, and the output is the value of the function, whatever that is. So these are two examples right here that kind of will help you out, but in general, this is true for any function of two variables. And it's really the same case for a function of three variables, or really any other number of variables. In this case, for a function of three variables, the input is now three values, x, y, and z. And this maps to whatever the function value is at every given point. That's the output, which is the function value at that point. And now it's a function of x, y, and of z, because this is a function of three variables in the n equals 3 case. So this gives kind of a summary of the notation and really what the main topic of study in this class. And like I said in the intro, what I'll be talking about as we move through the course, the first half of the course will be all how to generalize concepts from Calculus 1 from the derivative, so optimization and all sorts of derivative applications, and generalizing all of this stuff to multivariable functions. And the second half of the course will be all generalizing the definite integral to multivariable functions. So one of the first topics that we have to consider, that's a very important topic to consider, is how we define the domain and range of a scalar valued function. And for any multivariable function, even non-scalar valued multivariable functions, you can talk about their domain and range. But we're just going to right now go through how to solve for the domain and range of a multivariable function. So first I'll define what those are. So we'll say for every multivariable function, we can find a natural domain which we'll call D, and range R associated with that function. And specifically, we'll say that the functions that we're going to be considering are going to be functions from n-dimensional space into R. That's going to be a scalar function of n variables. Or typically, for many of the examples we're going to look at, n is going to be either 2 or 3. So a 2-variable function or a 3-variable function. These concepts can be extended to any number of variables for a function, but the idea is that many of the nice examples that we can kind of visualize and see are for 2-variable functions and 3-variable functions. So we say that the domain of a function is a set of points in n-dimensional space Remember, we're symbolizing n-dimensional space using the real number line symbol to the power n. That's what we mean by n-dimensional space in terms of just notation. So domain is a set of points in n-dimensional space where the function is defined. And I'm going to put this in quotes. What I mean by defined is it's nice. You don't get anything bad, like the square root of a negative number, or the natural log of a negative number, or the natural log of 0, or divide by 0, right? All of those things are bad things. We have to, when we're trying to find the domain of a function, avoid anywhere where that happens. So we'll see how to do this very clearly in a few examples as we continue on, but let me also define the range as well. So the range R of a function is a set of points in, we'll put on the real number line, right, and I'll also use a little bit of color here to denote here this D, the domain of the function, relates to this right here. It's a subset of n-dimensional space. It's a set of points where the function is defined. And the range of a function relates to where we're mapping to. In this case, we're mapping into the real number line. This is a set of points on that real number line, or it's a subset of the real number line where that f maps to, or that. or better yet, a set of points that get hit by f. So let's go through and see if we can figure these out and do a little bit of detective work on some examples. So the first example that I want to consider and we'll look at is going to be the example, we'll say w is equal to the square root of x squared plus y squared minus 4. Here our function, our multivariable function, is f of xy, which is this function right here, square root of x squared plus y squared minus 4, and this is saying that w is our output. It's a value in whatever we get when we plug in any values of x and y. For instance, if you were to take in here and plug in, we'll just do a little example. We'll do so at the point 2, 2, w is equal to f of 2, 2, which is the square root of 2 squared plus 2 squared minus 4, or the square root of 4 plus 4 minus 4, which is just the square root of 4 plus 0, which is equal to 2. So at the point 2, 2, this function is equal to 2. And what we want to first do always, whenever we have a multivariable function, is determine the domain and range of that function. So let's do this for the domain first. The domain of this function can be found by looking at the function and identifying any bad points of the function, or I shouldn't say bad points, any bad scenarios we might have involving the function itself. So specifically, any way the function itself may not be defined. In this function right here, we can see that we have a square root, and we have x squared plus y squared minus 4. So the x squared plus y squared minus 4 term is fine. There's no division, so there's no worries about possibly dividing by 0. But we do have a problem with the square root function, because we know that the square root function can only be taken on things that are greater than or equal to 0. So this gives us a restriction on our domain. Specifically, the restriction that has to be true for the domain of this function is that x squared plus y squared minus 4 has to be greater than or equal to 0. If this is not true, then this function, you end up trying to take the square root of a negative number, a negative value, which is not possible to do. So we have to conclude then that the natural domain of this function is all points where x squared plus y squared minus 4 is greater than or equal to 0. And what that means then is that x squared plus y squared is greater than or equal to 4 if you add 4 to both sides of this inequality. And remember that x squared plus y squared is the same thing as r squared, where r is the distance from the origin, the radius from the origin. Right, so for any point x, y, you'll hopefully remember from Calc 3 that r is the distance from the origin. So I'm just drawing a picture right here that's kind of showing this. So what that means is that the condition that we have, because remember 4 is the same thing as 2 squared, is that r, the radius from the origin, has to be greater than or equal to 0, and that the domain of this function is all points, and I'll actually keep this drawing. I'll move this drawing over a little bit so we can see this a little bit better. The domain of this function is all points outside the circle of radius 2. Oops, sorry. This is should not be 0, but 2. We get this by just taking the square root of both sides of this inequality. So we can kind of shade this in and see that directly. If instead of thinking of this as a general circle of its radius r, we take this to be the circle of radius 2, and then we shade in all of the points in the domain, which is all points that satisfy this inequality right here. So it's all of these points right here that are outside the circle of radius 2, and it's all points on the circle of radius 2, because this inequality is satisfied when r is equal to 2, when r equals 2. So this is the correct way of solving for the domain of this function right here. Now for the range, it's a little bit different. The range is asking for what values this function hits, or what values this function maps to. And what you can do for the range is always kind of view this as a composition. That's probably the nicest way of doing this. So if you view, say, u as being equal to x squared plus y squared minus 4, then w is just equal to the square root function of u. And what that means then is that if you look at the square root function for u, the square root function for u is only defined when u is positive. And specifically it looks exactly like this. This is the u-axis, say, and this is the w-axis. This is the function w equals the square root of u. Now we know that u only goes from, because u is x squared plus y squared minus 4, right, u goes from a value of 0 on the surface of radius 2. U is equal to 0 at any point on this circle right here. And u only gets larger as you move away. You move further and further and further away. So what that means then is that the range of the square root function, square root of u, is the range from u equals 0 out to u equals infinity, all the way out to positive infinity. And that then means that the range of our function f is going to also go from 0 to infinity. It's going from the interval from 0 to all the way out to positive infinity. And that's the range for this function. Sure enough, it's very nice to have tools to kind of visualize this and see this, and that's exactly what you can do. So throughout the course, I'm going to be using a combination of custom Python code that I've written, as well as showing you how to do similar things using two main online tools. So there's going to be two online tools that are very, very useful for you in terms of plotting and visualization. These tools are going to be what's called this software GeoGebra 3D, and the other tool is called Desmos. These are some of the fastest online graphing calculators and plotters to help you visualize things and visualize curves and see things in both 1, 2, and 3 dimensions. So GeoGebra 3D is what I'll open up now. I have a GeoGebra 3D window open along with my custom Python plot of this function that I'll generate. So I'm going to run the Python code right now, and I'll open up both windows. And we'll see that what we've done is verify exactly what I was talking about. So here we have side by side. On the right hand side is my Python output, and on the left hand side is my GeoGebra plot. You can see what I've entered into GeoGebra. I've entered in exactly this: z equals the square root of x squared plus y squared minus 4, and you see exactly what I'm talking about. So this is a plot of what's called the graph of the function. This is a big concept that we're going to be talking about, where at every single point in the xy plane, so any xy point you choose, the z coordinate is giving the value of the function at that point. So say if you take the point 2, 2, which is what we calculated the value of the function at 2, 2 before, that's about this point right here, 2, 2, right here. So this point down in the xy plane is 2, 2. At that point, it goes up to the z coordinate, which is the value of the function at that point, which is exactly the function value of 2. And this is true for every value of x and y. What's neat about this plot is that you also see a verification of our domain and range calculation for this function. Specifically, the domain of this function is all points outside the circle of radius 2, because these are the only points where our function is defined. And the range of the function is from 0. The lowest value of this function is 0, and it goes all the way up to positive infinity. You can imagine this surface stretching out and spreading out in many different directions, every different direction. So this is a very good example for a number of reasons. And I just included the Python plot to show another picture showing this verification. The plotter here is going from 0 right here up to infinity, and you can see all of the verifications that I told you about before, where the domain is the circle of radius 2, everything outside the circle of radius 2, and the range of the function goes from 0 to infinity. So that's going to be it for this lecture. We'll pick up here tomorrow and do a couple more examples, and then introduce the concept of traces in the next lecture. But thank you very much for tuning in, and I hope you have a great day.